Hey guys, welcome. So today we will talk about number theory. This will be the recitation 6 for number theory. I decided to have a full lecture, let's say, because I would like to cover more on some analytic methods in solving some number theory problems, but also I would like to do some congruence type of problems. Maybe I wouldn't go that far in doing more problems using quadratic reciprocity, although I had one in mind, but anyway, I don't think I can cover everything. All right, so let's get started. I would like to prove one thing, which is very important. Okay. Wait, where is it? Okay. Well, it's not quite October 9th, but anyway. Okay, the first problem that I have in mind, which is a very, I would say, very difficult problem, is to show that the set, and I'm going to define this set in the following way, the set A, which will be the fractions of all prime numbers, so P over Q with P and Q prime numbers. This is dense, whatever that means, and 0 infinity. Well, what dense means is that between any two real number, any two positive numbers, we can find a fraction P over Q. So that's what we have to prove. So we have to prove that we can find P and Q prime numbers such that for A and B positive, A is less than or equal than P over Q, less or equal than B. So that's what we have to prove. And before I even, frankly, I don't know a proof without the prime number theorem, basically. So we will use the prime number theorem, PNT. This is, in fact, a very nice result to know. And this prime number, the prime number theorem is hidden in the following lemma. First, we prove the following lemma. Okay. The lemma says the following: if I have two numbers, let's say A greater than B greater than 0, then the limit, let me write it here, as x approaches infinity, of pi of AX minus pi of BX is actually infinity. So that's the lemma. Well, as you can imagine, when we have problems like this, the first thing that comes into our mind is to show that, to use the prime number theorem. So let's see proof of the lemma, and the problem will follow easily from the lemma. So we want to use the prime number theorem, and let me just say it, which says that the limit as x approaches infinity of pi of x over x over log x is 1. So that's the prime number theorem. Keep this in mind, right? Okay. Let's use this. So this implies that the limit, let's write it in this way, as x approaches infinity, of pi of ax minus pi of bx over x over log x. So you see I'm going to write it in this way. And what I'm going to do here is the following. So I will write this in the following way. So bear with me. This would be pi of ax over log of ax, as you can see. So I'm writing in this way, times, and now I'm multiplying by a log x over log ax. And now I'm going to write here the same thing, so minus pi of bx over log bx. And now I'm going to multiply in the same fashion, b log x over log bx. Okay. Can you see it there? I squeezed it a bit. Is it clear for everybody? So this guy here is b log x over log bx. Okay. Now, what can you tell me? In the virtue of the prime number theorem, this limit will be equal to what? So here using the prime number theorem. This limit is what? Can you tell me? For example, this one here, this limit is equal to what? Can you tell me? As x approaches infinity, this limit will be what?
It will be 1, right?
Not 1, pay attention. It's actually, no. Yes, it's 1, right? Okay, correct.
A is just a constant, right?
Yeah. What about this one? This will be what is this? The limit of this as x approaches infinity is what? Is what? Can you tell me? Is a, right? And the same goes for this one. This will, by the prime number theorem, is 1. And this will be b, right, as x approaches infinity. Okay, so the result will be a minus b. You see? Okay, so we have used because, let me write it again. The limit as x approaches infinity of pi of ax over log of ax is 1, just like Aaron said. And the limit as x approaches infinity of log of x over log of ax is 1.
So I have a question.
Right? Yes.
So maybe you can answer this at the end because I don't want to cut you off. But how do we get the prime number theorem?
Well, you apply the prime number theorem here.
Yeah.
We don't get the.
What I'm saying though is like, what part? Where is that coming from exactly? I mean, that equation.
Which one? This one here?
Yeah, the one we used to simplify basically down to a and b, a minus b. And
where does this come from?
Yeah.
Well, just look at the lemma, what we were trying to prove. We're trying to prove that this difference is large enough. So that's why you're trying to express this difference here, you see? But you try to express this difference in terms of the prime number theorem. So you're trying to make it look like the statement of the prime number theorem. As you can see, the prime number theorem has this guy here, x over log x. Right? Does this make sense?
Yeah.
Okay. So the proof of the lemma is done, right? So that ends the proof of the lemma, but not of our problem. Okay. So now what we're trying to do is to veer towards the problem. So we know that let's look at the lemma. We know that this guy here, this is true. And for a greater than b greater than 0. Now we're trying to make use of this, so let's write it. So we can say that, so this implies that for all epsilon positive, and let's just say with epsilon less than the difference between a and b, less than a minus b, there exists a delta positive such that pi of ax minus pi of bx is greater than a minus b minus epsilon times x over log x, right? So we can say that, right? Just look at what we proved. We look at this difference, so we prove that this pi of ax minus pi of bx is greater than, well, since the limit is 1, so then x over log x times a minus b. And it follows, the lemma follows immediately. And the conclusion of the lemma, maybe I rushed through things by saying that I proved it, but, and the lemma follows immediately. Okay, now we can say we proved the lemma. And now, let's see how we prove our problem. So how are we going to show that? So now, going back to our problem, right? We have to show that that in the interval, and let's just say I'm going to denote this interval by this way, BA, right? Right, for wait, that for all, okay, let me be just a second, that for all a greater than b greater than 0 in the interval, let's just say BA, right, because b is less than a, okay, there is at least one element of the set A. Okay, right? Keep in mind that the set A is given by this. Okay. All right. Now what we're going to do, so by the lemma, by using the lemma, we pick a prime Q, let's say. We pick a prime number Q. This is Q, not G, such that pi of AQ minus pi of BQ is greater or equal than 1. So this is by the lemma. So there, we can say that there exists a prime number. There exists a prime, let's say P, such that B times Q is less or equal than P is less or equal than A times Q. Or you can say that A is less or equal than P over Q and less or equal than B. And that's it. This is what you have to prove. There's the problem, right? So between any two positive numbers, you can find a fraction of this type as a fraction of prime numbers. And this is the proof of this. You see, I wanted to show you an application of the prime number theorem. This is like the heavy artillery I use here, the atomic bomb, I would say. Prime number theorem is such a tool. So it's like dropping an atomic bomb to and basically you kill everything. That's how strong this prime number theorem is. And you can see you prove something very, very strong. You prove that these fractions that look like fractions of prime numbers is dense in zero infinity. Probably you know this result that Q is dense in R. Maybe I should mention this as a remark, but we will cover this more when we'll do analysis. So let me point out a remark. Q, the set of rational numbers, is dense in R. Anyway, I'm not diving more into this since it's going towards analysis, and I want to stick to some number theory. All right, so that's problem one. Now problem two that I wanted to show you is the following. This is a difficult one, and it involves analysis. Okay, I will discuss it, which says the following. Let C be a real number such that this guy n to the power c is an integer for every positive integer n. Okay? Show that this C, this real number C, is in fact a non-negative integer. I want you to look at this problem for a bit, and I would say maybe I should mention the source as well. So this was a Putnam A6 9071. I want you to look at it and tell me if you have like an idea. How would you approach such a problem? You see, you don't know where to pick this, how to pick this problem. Like,
I have a comment.
Yeah, please.
So if C is non-negative, could you do proof by contradiction and show that if C is negative, you get a fraction? And
yeah, that would be an idea, but that would be the start. Yeah. But you see here, well, this problem will involve like heavy analysis here. Let me just look at the case n equals 2. So when you have a statement like this, which says that for every positive integer n whatever, maybe you should see what happens when n is small enough. So let's look at the case n equals 2. What does this case n equals 2 tells us? This shows that C will be non-negative. That's obvious, right? Since it's for every positive integer n, well, let's take n equals 2 to the power c is an integer. Well, I don't think c can be a negative, because that would not be an integer. So, right, you see you have the exponential that would be between 0 and 1, correct? 2 to the power c. If c is is negative, then 2 to the power c will be less than 1. But that wouldn't be an integer anymore. So that's clear that c is non-negative. But now, so from n equals 2, it follows that c is non-negative. But we want something even more. We want this to be a non-negative integer. So that's the hard part to show. So at this point, we have to show that c is an integer. And let me tell you one thing, and I think I've discussed this, those of you who have taken advanced calc with me last year, and I know there are a bunch of you here. Remember when we talked about the mean value theorem? So remember, let me recall. And the mean value theorem, and we will do this in analysis as well, Theorem of Lagrange, which says the following, that if I have a function f defined, let me write it in this way, f defined on a closed and bounded interval AB is differentiable on AB, continuous on the closed interval AB, then we have that, remember, we have that f of b minus f of a, so this average over b minus a is nothing else than just f prime of c, right, for some c in AB. So this is the mean value theorem of Lagrange. Keep that in mind. And we will see that we would like to see how, well, first of all, let's apply this. So apply now by the mean value theorem. And I will abbreviate this by MVT from now on. Applied to the function. And this function that f of x, let's say x to the power c, right, on the interval. And I'm going to take this interval u plus 1, so 2 consecutive, right? There exists, let's say, this guy c, so I don't want to use c, right, because from u plus 1, such that, I'm using more Greek letters, I hope you don't mind that. So by the mean value theorem applied on this interval, right, there exists a c from in the interval u plus 1, right, such that, well, such that we have the following. So we have f of u plus 1. Okay, let's write it. F of u plus 1 minus f of u over u plus 1 minus u, so that you can see how I applied, is f of f prime of c, right? Keep in mind that this c, in fact, I already said, so I don't need to mention it again. Okay, but this guy is equivalent with, if we want to write it, right? This guy is equivalent, keep in mind that our function is this. Don't forget that. This is our function. So now if we apply this, it follows that we will have that u plus, we can write this as u plus 1 to the power c minus u to the power c is nothing else than just f prime, which is c to the power c minus 1. So this is what we get. Right? And now, what can you say here? when you look at it. So can you say something? Let's see, for any positive integer u, right? What can you tell me about the left-hand side? What is the left-hand side? So the left-hand side is a what? Is a positive integer. That's obvious. So I'm just subtracting two positive integers, but the thing is that u plus 1 to the power c is greater than u to the power c. So that's a positive integer. Okay. So I know that this is a positive integer, keep that in mind. But now in the case, so I want to show that, so from here, I would like to, so it will follow that c times c to the power c minus 1 is a positive integer. So the only thing I have to show is that that's this guy c is not in between 0 and 1. So now if we take c to be in the 0 and 1, so in the case when c is between 0 and 1, right? I want to exclude this case. U could be taken large enough, so we can take u to be large enough so that this will imply that u to the power c minus 1 is less than 1 over c. So this guy, c times c to the power c minus 1 is less than 1. But that's a contradiction. So this is not good. This case is not good. You see, because this guy is less than 1, but also is a positive integer. So this means that it should be, can you tell me a positive integer, which is between 0 and 1? And not 0 and 1, well, there is none. So we get the so this means that c is greater or equal than 1. But you see, so c is indeed an integer, right? We proved first that c is non-negative. C cannot be 0, right? Well, this is positive here, not greater or equal than 0. Let me be specific. Okay. So at first we proved that that is non-negative, so it cannot be 0. And now we show that it cannot be between 0 and 1. So it has to be greater or equal than 1. Beautiful. So, and it's an integer. Okay. Now, because I want to go further, I would like to, well, I would like to extend it somehow. So now we would like to, we would like to extend the mean value theorem. So now I know that c is greater than 1. So I have to, well, let me rephrase that one. I know that c is greater than 1. And I have to show that actually it's an integer. But now this mean value theorem is not enough. So we would like to extend, that's the trick here to this problem, the mean value theorem in the following way. Let me explain it. Because I want to extend this to higher order derivatives. And I will explain this in great detail. I want to show you exactly how things work. Let me write it in this. If let's say if f of x is k times differentiable, on the interval, let's say a, b, then, how should I say, there exists let's say C in AB, I don't want to use C, such that we have the following, such that this guy h to the power k, and I'll define immediately, times the kth derivative of C is equal to this delta k f of A. All right, let me explain now. Where h is nothing else than just b minus a over k, and delta k is the, let's say, k difference for intervals spaced h apart. Okay. And now let me explain this a bit. Let us explain. I want to explain this in great detail. Let's explain things a bit. Okay. Look at it. Well, let me explain this delta k. First of all, we define that delta f of x, and you will see here that this is like a difference operator, is f of x plus 1 minus f of x. It's what we call, if you want, the discrete derivative, if you want to use it like this, or the difference operator. Now we can iterate delta, iterating delta. We have, let's say, delta square of f of x. So this will be delta f of x plus 1 minus delta f of x. And if you want to write this, this will be nothing else than just f of x plus 2 minus 2 times f of x plus 1 minus f of x. Right? It's f of x minus I think it's plus here, right? So it's f of x plus 1 minus f of x minus f of x plus 1 minus f of x. Anyway, and now by applying the mean value theorem, so it is quite clear that by the mean value theorem, so we apply mean value theorem step by step, basically inductively. It follows that delta squared of f of x is the second derivative now of f at the point c for some c between x and x plus 2 this time. Right? So, and we keep going, right? And we keep going. So inductively, we can say that we can show that delta n f of x will be the nth derivative of f at the point. Well, I'm taking the same c, but it's a different c. So for some c, and now between this interval x plus k. I'm sorry, x plus k. Right? Again, this is the mean value theorem. Okay, x plus n, sorry, because I have the n derivative here. Okay. So that's what we're going to do. So we're writing this difference operator, we apply the mean value theorem, and we keep going like this. Okay, and now let's go back to our problem. So this is the procedure. Keep in mind that we want to use this. Well, it's like I said, it's a tricky problem. Now, going back to our problem, we want to take, let's take k as the unique integer such that k minus 1 is less or equal than c and is less than k. Okay. And now we apply the mean value theorem, right? The extended mean value theorem. So apply the extended mean value theorem on the interval u plus k. Okay, and now we know this. So this is this implies that we obtain the existence of, let's say, a point C again, but it's not the same C from x plus k such that, and we want to apply the extension. The nth derivative of that will be c times c minus 1 times c minus 2 times all the way c minus k plus 1 times c to the power k c minus k, and this will be the delta k of f of u, right? All right. So now what we were trying to prove is that, well, keep in mind that this will be an integer. And now by taking u sufficiently large, so basically we apply the same idea as we applied from the case when we applied the initial mean value theorem, right? So we want to do the same thing. So by taking u sufficiently large, we have that it follows that c to the power c minus 1 becomes sufficiently small. Okay, so that the left-hand side, when I say the left-hand side, I mean about this guy here, right, is less than 1. Less than 1. Although it's non-negative, which is, again, not good. So this means that C times c minus 1 times c minus 2 times all the way c minus k plus 1 will be 0. So c will be k minus 1, and that's it. This is an integer. And since we show that this is non-negative, this is a non-negative integer. And that's the problem. Man, I spent a lot of time with this problem to figure it out, and it was a pain in the neck, I would say. It was very difficult. Oh, what's going on? Just okay. It was very difficult, I would say. Sorry about that. Well, is it clear, at least the procedure? Anyway, let me do another problem. In fact, I'll leave this to you. Let me see how much time I have. Maybe I'll leave it at the end, this one. It's again, it uses some analysis. Or maybe no, okay, let me do it now. So problem 3. And I'll just tell you the main steps. This was, let me see. So this was problem, okay. Problem 3 says the following, has a long statement, says the following: define a positive integer n to be squarish. You'll see immediately what this means. If either n is itself a perfect square, or the distance from n to the nearest square is a perfect square. Okay. For example, let me take the number 2016. So for example, 2016 is squarish. And let's explain why this is it's squarish. Because the nearest perfect square so the nearest perfect square to 2016 is 45 square, which is 2025, and 2025 minus 2016 is 9, which is a perfect square, right? And of course, let me of the positive integers, between 1 and 10, only 6 and 7 are not squarish. Are not squarish. Right? So do you understand the definition of a squarish number? Is it clear for everybody? Jack, is it clear? Aaron? Okay. And now what we're trying to do is, now we're getting to the statement of the problem. So this was just a preamble of, so for a positive integer n, let's say, let S of n be the number of squarish integers right, between 1 and n. Inclusive. So I will include also n. Okay. And now what we're trying to do, we're trying to see the asymptote so for Sn. So the question is the following: find positive constants alpha and beta such that the limit as n approaches infinity of S of n over n to the power alpha is beta. So that's, you see, that's the statement of the problem. Give me 1 second. Okay. And let me tell you the main ideas. I'm just going to tell you the main ideas. And the thing is that you can actually count them directly. So I'll leave this to you. So the main ideas, let's say the first one is a direct count shows that we have the following: S of m plus 2m is nothing else than just m plus this sum, the sum from k equals 1 to m. And pay attention here, I'll have, well, 2 times the nearest integer of square root of k, right? So that's the formula. You first prove, it's just a count. And let me give you some reasons why this happens, since the interval, let's say if we look at this interval k squared and k squared plus 2k, has exactly 1 plus 2 square root of, and the nearest integer square root of k squarish numbers. So that's the reason. Okay, so now you have this. And now another ingredient which we will prove in our analysis, but I'll leave this to you. We have the following estimate. The following estimate holds true. And like I said, we can prove this by using Cezar, for example, but anyway, I'm not getting into details at this point. Okay, let me write it like this. So the sum from k equals 1 to m of the square root of k is nothing else than just 2/3 times m to the power 3/2 plus some o of m, right? So as m approaches infinity, that sum over there over m to the power 3/2, sorry, is 2/3. Anyway, we will prove this using Cezar. And now, once we have these two ingredients, this implies that well, by combining these two, look at them. You see, we have here, we have this. We will use the estimate on this. So by combining these two facts, we will have that S of, let me write it like this. We will have that S of m squared plus 2m will be something like 4/2, right? Because there is a 2 here, keep in mind. 4/2 times m to the power 3, 4/3, sorry, times m to the power 3/2 plus an O of m. And now, anyway, the final step is to, that for a general, let's say x, right? If we take m to be the nearest integer of the square root of x, right? And then we will have that s of these two guys, s of m squared plus 2m and s of x. They don't differ that much, so they differ by an O of m. So with this observation, it follows that, so we have that s of x is nothing else than just O of square root of x plus 4/3 times square root of x, everything to power 3/2. Or if you want to write this, this would be 4/3 times x to the 3/4 plus O of square root of x. So the answer is given by, so we can deduce that alpha and beta, now if you want to write this, is nothing else than just 3/4 and 4/3. And that's it. All right, so these are the main steps. Is it clear for everybody? Now I'm just lazy to count all this here, the direct count, but anyway, I think you can do it. It's just, you can just have to write the definition of the nearest integer, what the integer part is, and so on. Okay. Honestly, this, I forgot to say, this was a Putnam B2 in 2016. I would not rate this as a B2, honestly. Maybe a B3. I think it was a bit hard for a B2, but anyway, it is what it is. That was the problem. All right, so I think I want to do more now with other problems. So I think you have seen some analysis here, how to use analysis in number theory. Now let's see problem 4. I want to keep to some modular arithmetic. And another problem that I have in mind, and I would like to show you some things on how to use type modular arithmetic modulo P more. So the first problem, and it's a problem on our list, is that to prove that PA choose PB is congruent with A choose B mod P for all integers. P, A, and B with P prime P0 greater than 0 and A greater or equal than B greater or equal than 0. All right. I want you to look at this. Think about it for a second. This was a Putnam A5 in 1977. All right. I want you to think for a couple of minutes while I'm running to the restroom. I'll be right back. Don't run away.
I'm going to run away.
Okay, let's see. Give me 1 second. All right, so let's see. Do you have any ideas? So how would you approach this? So you'll be tempted to write that P A choose P B. Well, just plug it in, right? So the first thing, this was a Putnam 8.5, but honestly, to be honest with you, I think this is much easier than the previous problem. So the first thing that we need to know, so we keep in mind that, well, let's write it. It is well known that that P choose I, let's say, is congruent with 0 mod P for I between 1 and P minus 1. That's obvious, right? And we have seen this. Or let's translate this in an equivalent language. Equivalently, we can write this. We can say that in ZP, that in the field of integers modulo P, we can say that in ZP of X, right? So, and let me say that this ZP is the field of integers modulo P, right? So the ZP has these elements, 0 all the way to P minus 1. So we can say that in ZP, we have that one plus x to the power p, and everything to the power p, is nothing else than just 1 plus x to the p. We can say that, right? Okay, so this follows that, and I'm gonna do the following thing. And this is the trick of the problem. So we have that, and I'm going to do the following. I'm going to look at this guy, 1 plus x to the power pa, everything to the power pa. At one hand, by expanding this as the binomial directly, this will be nothing else, the sum from, let's say, k equals 0 to pa of pa choose k times x to the power k, right? By the binomial expansion. But on the other hand, I can do the following trick here. I can write this as 1 plus x, everything to the power p, and I know who this guy is, look here, everything to the power a. So writing this, putting this in here, it will give us the following. It will give us that 1 plus x to the power p, everything to the power a. Wow, that's beautiful. And now I can expand this to binomial expansion. I can write it, and this will be nothing else. Let's just say the sum from j equals 0 to a of a choose j x to the power g jp. So at this point we have this equality here. You see, we have this is the same with this modulo p. And now we just have to look at the coefficients, and that's it. We're done. So since how should we phrase this? Since coefficients of like powers, let's say, must be congruent modulo p, it follows that in the equality. So this is in ZP. I want to make myself very clear, right? ZP of x. So everything is modulo p. So in the equality, let's write this equality, the sum from k equals 0 to pa of pa choose k x to the k is the sum from j equals 0 to a choose j x to the power jp. So in this, so this again in zp of x, I want to make my, we can see that one can see that this guy here, if you look at this guy here, right? If you look at the last one, it will be the same with this last one. So here I should put for k equals, let's say pb. So, and this is for k equals b, for j equals b, sorry. So we see that this will hold true, that PA choose PB is the same as A choose B modulo P. And pay attention for B, taking all the values for 0, 1, all the way to A. So that's it. Maybe I should erase this garbage here because it goes from all of them. Okay, I think it's clear now. And that's the end of the problem. Is it clear for everybody? Jack, is it clear?
Yeah.
Was it tricky or?
No.
Not that tricky, right? If you know how to, in fact, you can smell the problem, like, okay, it's quite clear that I have to look in the field of integers modulo p. So it's kind of, I'm sure you would have done this by yourself easily. All right, now I have one more problem to go. I'm sorry I'm going a little bit faster, but anyway, I want to finish this. And the other problem I want to do, that's again, it's a problem B4 this time. So this is problem 5, and is the following. It says the following. Let P. It's our. I think it's problem. Problem 20 in our list, I think. And it says the following. Let P be an odd prime show that the sum from j equals 0 to P of P choose J times P plus J choose J. So this guy here is congruent with 2 to the power P plus 1 mod P squared. Okay. And this was a Putnam before, a more recent one, before 1991. Well, you would say like maybe we should, the first thing that will come into your mind will be like, okay, maybe I should just compute that, maybe there is a way for me to compute this guy. Well, sure, maybe there is. In fact, I think there is. Anyway, I gave you some kind of a Vandermonde type of identity when we had in our combinatorics lecture. I think it was the first one, if I remember correctly. But I don't want to be too much. I mean, you have to know all these kind of identities. So if you don't know any kind of identity, maybe we can just use some modular congruences. And I think I gave you one. And let me, ouch, what did I, oh my. Oh, we also have the black here, that's good. So solution. In a previous lecture, we proved that, and I'm going to write it in this way. What did we prove? We proved that, remember that 2 for a prime number, 2p choose p minus 2 is divisible by p squared. Remember that thing? So we proved this. Do you remember? Anyway, so we proved that that was our first lecture in number theory, that 2p choose p is congruent with 2 mod p squared. So this was proven. So we would like to use this. And we're going to do the following. And now let's look at that sum over there. So now we have that this sum here, the sum from j equals 0 to p is p choose j times p plus j choose j. And I'm going to do the following. Look, pay attention here. So I'm going to drop the first term for j equals 0 and the last term for j equals p. So I'm going to leave them outside. So the first one will be 1, and now I'm going to write the sum as the sum from j equals 1 to p minus 1. And now I want you to pay attention because I want to do some magic trick here. What I'm going to do, I'm going to work on this guy over here. I'm just going to write it. And this will be p plus 1 over 1 times p plus 2 over 2 times all the way p plus j over j. Okay, plus, and the last term, right, for it was 2p choose p. So that's the trick, to leave out the last term, because these are complementary binomials, right? You know they're equal, right? Well, n choose k is the same as n choose n minus k, right? So the last term will be this one. So let's keep this in mind because I want to use it at some point. All right. But now let's work a bit with these guys. I want to see what's going on here. especially when I have something on the denominator and I'm working modulo something. So basically I'm talking about the inverses. Now keep in mind that modulo P, this is important, the sets, let's just say from 1 all the way to P minus 1, and this set, U 1 inverse, 2 inverse, all the way to P minus 1 inverse, these two sets are the same, right? Where the inverses, keep in mind that the inverses are taken modulo P. Are taken modulo P. Modulo P. All right. So let's keep in mind this. And now, although the inverses one inverse all the way to P minus 1 inverse are only defined modulo P, right? They appear multiplied by P. So they appear multiplied by P. Okay. And now finally we have, so I can write that sum in the following way. So we have that 1 plus this sum from j equals 1 all the way to P minus 1 of P choose j times, and I'm going to write this P plus 1 over 1 times P plus 2 over 2 all the way P plus j over j plus this last term 2 P choose P. This will be congruent, and I'm going to write it in this way. Since the set of 1 and the set of the inverses are the same, this will be not modulo P. This will be nothing else than just 1 plus the sum. So that's the main observation here that we need to take into account. P choose j, and here I'm going to write it in the following way. So as you can see here, I have over 1, so I can write this as in the following way. So this will be 1 inverse times P, P inverse. So this would be negative 1 inverse times P plus 1 times 2 inverse times P plus 1 times J inverse times P plus 1. Okay? And I'll have here plus 2, right? Okay, so now once we have this, this is nothing else than just 1 plus, so these guys will be, modulo P will be just 1, right? All these guys here. So this would be the sum from j equals 1 to P minus 1 of P choose j plus 2. And here we use the fact that P divides P choose j for j between 1 and P minus 1. Okay? And this will be further equivalent with, right, with what? Wait, I forgot to say, you see, I used here, oh my, I used the lemma, right? This guy, look, I used the fact that 2p choose p is congruent with 2 mod p squared, right? I use it here. So here we use the fact that 2p choose p is congruent with 2 mod p squared. Okay. And now finally, this will be nothing else than just, well, if you want to write it, this will be the sum from j equals 0 to p now, if we want to include that 1 2 as well. So we will have that this is P choose J plus 1. But this guy, you know that this is 2 to the power P. So this will be nothing other than just 2 to the power P plus 1 mod P squared. So everything was mod P squared here. So everything, okay, we can write here mod P squared, mod P squared. So everything is mod P squared, everything. Anyway, so you see we have used this fact here. Yeah, I'm a little bit over time, but anyway, this is one of the crucial steps that we used. And in fact, you know what? I'm going to point out a remark here, and this is an important result, especially for those who are doing super congruences these days. So in fact, there is a stronger congruence which says, in fact, with Walston, sorry about that, Walston-Holm theorem asserts something even a bit stronger, asserts that we have that if P is greater than 3, is a prime, then 2P choose P is in fact congruent with 2 mod P cubed. We have this. We have something even stronger. Anyway, there are some other congruences as well, but I don't want to mention them. And I think I'm gonna stop here. So I have a question. Was it clear, Jack? Was this the problem clear, the solution?
Yeah.
What do you think? Was it tricky?
A bit. I think you gave me that problem last week to work on. I got fairly close, but I couldn't.
Oh, okay, that's good. That's good. Okay, I think I'm gonna stop here for today. I'd like to thank you very much, guys. Let me just say one more thing. Next week, so I'll post this video and then I'll post some other videos for the abstract algebra, and then I'll do a recitation for the abstract algebra. Probably I'll do it tomorrow. Next week we'll start something new. Probably you're already used with this by now. We'll start doing talking about linear algebra for a while, and then we'll do analysis, and that's it. All right, guys, thank you very much. I'll see you next week.